Okay, so connecting vector and parametric equations to 2 points. So this time we don't have a directional vector. They've actually just given us 2 points that do occur on the same line. They want us to make a parametric equation and a vector equation of this. So we're going to write down our equation so we can try to figure out what we're going to need to find. Remember, our vector equation was equal to r naught plus a scalar parameter of our directional vector. This is also written as y is equal to x naught, y naught, plus t ab. And the parametric form of our equation was x was equal to x naught plus ta, and y is equal to y naught plus tb. Okay? So, are either of these points representing our directional vector? No, neither of these points. They are 2 points that lie on it, but we don't know our directional vector. So we're going to actually have to go ahead and solve for our directional vector in this equation. What we're going to do is, since this is equation, or we'll call it equation EF, or directional vector for EF. Remember in the first question we said we could do it for both. We're going to take these points. So very similar to what we did in example 1. We're going to take the 2 points EF, and we're going to use the equation x2 minus x1 and y2 minus y1. And that's going to give us our A and B, or our directional vector. We'll call it our directional vector. Okay. So our F being 0.2 and our E being 0.1, x2 is 6, subtract -1. And y2 is 11, subtract 5. This gives us 7 and 6. So our directional vector for EF is 7, 6. Okay? Or our AB, you could say. So when we go to actually put this into our equation now, we'll put it in our vector forms first. Our vector form is equal to, now for our R naught, either of these points, because they both lie on the line, are acceptable. I could write the equation with point E, or I could write the equation with point F. Okay? Both of them will hold true. So let's use point E for now, since it's the first one, -1 and 5. Okay? And remember, that is our R naught, one of the points along the line, plus T, and our AB, or our directional vector, is at 7 and 6. So we're in component form right now for our vector equation. We've done that one. They also want us to write the equation in parametric form. So in parametric form, it may be easier if we convert vector R to its components. X and Y is equal to -1 and 5, plus T, 7 and 6. Okay. So remember, we are finished our vector form. This is one of the things we needed to find. Our component form, or sorry, parametric form. We then take x is equal to -1 plus 7t. And our y value, y is equal to 5 plus 6t. And these will be our parametric forms of the equation. Let's do blue. So that's part A of the question. We found our vector form and parametric form for the equation. We had to do a little thinking in it. What are the coordinates of the point where this line crosses the x-axis? Okay, so that's part B. Part B asks us, what are the coordinates of this vector when it crosses the x-axis? Okay. Now, when we cross the x-axis, let's try to think about what happens there. So, we have our two-dimensional grid. We're crossing the x-axis. Do we know part of a coordinate? 0 for which? The x or the y? The y, that's right. We know wherever this line crosses the x-axis, our y value will be equal to 0. Okay? So what we're going to do is we're going to look at our parametric form of the equation again, and we're going to substitute 0 in for y, solve for t, and then plug that t back in to solve for the x in the other part of the equation. So we'll zoom back in for part B here. So if y0 is equal to 5 plus 6t, t is going to be equal to negative 5 over 6. Okay. So we have that part. That was our y part of the equation. We then take the x part of the parametric equation, negative 1 plus 7 times negative 5 over 6. X is equal to negative 1 plus, minus 35 over 6. X equals negative 6 over 6 minus 35 over 6. X is equal to negative 41 over 6. Or what is that? 7 and 5/6? Is that right? Yeah. Negative 7 and 5/6. Oh, sorry. You're right. It is 6. 5/6. Good. So we quickly went through that one. Because we know y is equal to 0 along the x-axis, we plugged that in for y. We then found a parameter or a value for our scalar, negative 5 over 6. We plug that back into for the t in the other equation and solve for our x value. So this means this line would cross a little past or almost at negative 7, just past negative 6. Okay, and okay, now they've also given us another vector here. Okay. They said, can equation, and we'll write the equation out on the next page. Can this equation stand for the exact same line? Okay. Vector r, negative 15 and 7 plus t value of 14 over 3 and 4. Okay, so we're asking about this question here. What we need to find out, first of all, if these two directional vectors are other equation. Remember we said we could use any point. We used negative 1, or our e value, negative 1 and 5 in our vector equation. Sorry, negative 1 and 5, not negative 5. Plus, and our directional vector was 7, 6, right? Okay. What we're going to do is first of all find out if our two directional vectors are the same. Okay. Are these two directional vectors, this part here and this part here, the same? If they're not going the same direction, we're definitely not talking about the same line. Okay. So in other words, is one a scalar of the other? So can 14 over 3 and 4 be equal to some scalar of 7 and 6. Okay. In other words, we could also say that this x and y value, can this x value be equal to TA, and can the y value be equal to TB? We'll plug these values in. 14 over 3 is equal to t, and our a value is 7, so 7t. Okay. And does the same thing hold true for the number 4 and 6t? Well, in the first, or in the second one, t will be equal to 4 over 6. And in this one, t will be equal to 14 over 21. Is that right? 14 over 21? Yep. And do these two equate to each other? Fastest, we could change them into fractions with common multiples, or we can divide them quickly. 666. Boom. And these are scalars of each other. So we know we have the same direction here. That's good. We have the same direction, so let's try to make sense of that there. Our directional vectors are the same, but just because our directional vectors are the same at, let's just say for instance it was going this way, our directional vectors are the same for both questions. There are an infinite number of parallel lines to this. So they could have a directional vector going through here, and maybe this is the point they're going through. And we could also have the exact same directional vector down here, parallel to it, going through a different point, okay? Which means they wouldn't be the same line, they would just be lines that are parallel to each other. So we figured out that the directional vectors are the same. What we can do is now plug in, there's a couple ways we can do this. What we're going to do is we're going to plug in this value into this equation here to find out if we can get that point using our parametric form of the equation. And remember, this could also be written as our x and y, and these will be our x and y, okay? Our parametric forms of the equation where x was equal to negative... Same place. Did I give us a different number for the equation? No, I think it's the same one. Sorry, let me bring up both of them so I can see. That, okay, negative 1. Yeah, okay, it was good. And 7t. And y was equal to 5 plus 6t. Good. So, like we said, we're going to plug this in for our x and our y and see if our t's hold true. So negative 15 is in for our x is equal to negative 1 plus 7t. When I bring that over, it's negative 14 is equal to 7t. T equals negative 2. And let's see if that holds true for our y. The y value was 7, so 7 is equal to 5 plus 6t. Oh, does it? In the book? Oh, thank you. Okay, sorry, the question says negative 7. So let's negative 7 equal 5 plus 6t. When we bring the 5 over, we get negative 12 is equal to 6t. T again is equal to, oh no, negative 2. Okay? So, what we just figured out, nope, I liked what we had. Okay? What we just figured out is these are exactly the same line. Their directional vectors were the same. That's our first way of checking it. And the second line goes through the exact same point, which means that our second line would go through the first point as well.